Hey everyone, welcome back. This is example 10.8, and we are still dealing with ballistics and bullets being fired at wooden blocks and everything. And we're still in the part of the chapter where we're dealing with inelastic collisions. Here we don't have a bullet being embedded in a block. We do have a bullet, however, being passed through a block right here, and there is some loss of energy. There's a total momentum transfer, but there's some loss of energy. But the bullet keeps moving, but the block does as well. Whereas beforehand, the bullet was in motion. Here, the block was stationary. Here, both of them are in motion. Okay, so we have a mass of our bullet, which we'll write down, and a velocity that it's moving at, and we have a mass of the wooden block. And so the bullet passes through it. They're both moving, the bullet being moving at 125 meters per second. And the big question is, how far will the block slide before coming to rest? Well, that's quite a jump, actually. We're going to start this problem with momentum, what we know about momentum, but immediately saying how far will this block slide before coming to rest, that's quite an awful big jump. So what I thought might be more helpful is if we cross this out, and don't get too excited, we're going to come back to it, but we're not going to make that the very first question. But we're going to do this in little pieces. We're going to state things like this. Let's make little small goals. What's the velocity of the block after the bullet has passed through? Okay, so the velocity of the wooden block right here. Okay, and then we're going to make another goal to find out what's the net force acting on this block to bring it to a stop. And if you think about it, if you have a block or anything and a tabletop, say it's a block, say it's your phone, I don't know, and you slide it across the tabletop, what's bringing it to a stop? Well, you can probably figure out that it's friction. We want to find out the quantity of that so that we can find our final answer, which is then, now how far will the block slide before stopping? I think if we do this in little pieces, A, B, and C, it's going to be much more manageable. Okay? So let's get started. We want to first find what the velocity of the block is after the bullet has passed through. So I'm going to go back here and actually erase this. And by the way, I wrote this. Here's my little diagram right here. So here's the bullet before the block, and then the block moving and the bullet moving. And this I wrote as this is delta x. That's ultimately what we want to find, how far this block is going to move. But all this I'm going to erase just now for the time being, so we have a little more space to write. Okay, so let's do part A first. We want to find the velocity of the block. Well, we can do that by using conservation of momentum. We know that there is momentum, initial momentum of the bullet, and there's initial momentum of the wooden block, which you're probably thinking that's 0, which it is. And that's going to be set equal to the combined momentum afterwards. The momentum final of the wooden block, which there is momentum now because it's moving, and the momentum final of the bullet. Well, and like you were probably thinking, well, tell you what, I'm not going to write that quite just yet. Let's break this out into our components that create momentum. That's mass and velocity for each one. Okay, so we're going to have our mass of our bullet times the velocity of the bullet plus plus quantity mass of the wooden block times the velocity of the wooden block. Here's where you're going to say, oh, hey, look, the initial velocity of the wooden block is 0 because it's just sitting there, right there. So that's going to go away. And then we have, after the equal sign, we have our mass of the wooden block, assuming there's no mass lost. Now, usually when you shoot things with bullets, it loses some mass, but we're assuming that it's the same mass, despite maybe having a hole in it. And this is going to be our velocity final of the wood block, plus quantity, which is a mass of the bullet, times the velocity final of the bullet. I probably should have written initial velocity in there for bullet, but of course this right here goes away anyway. So, all right, well, let's write down our knowns, and we should be able to do that fairly quickly. We have the mass of the bullet. That is, where's my equal sign? There it is. 75 grams. But we want kilograms, so we're going to have to move our decimal point 3 places to the left, right? That's 0.075 kilograms. Okay? Mass of our wood block is 2.25 kilograms. That's already what we want. 2.25 kilograms. It's already in the units that we want. We have the initial velocity, VI, of the bullet. That's 450 meters per second. And we can probably figure it out, and you have already, that the initial velocity of the block is 0, because it's just sitting there. Okay? This coefficient of kinetic friction over here, we'll come back to that a little bit later. Okay? We don't need that quite just yet. That's going to be, we're going to deal with that in part B and part C. Right now, we're focusing on the velocity of the block after the bullet has passed through. Okay? So, this right here, that right there is what we want to find. So, let's start getting this by itself we're going to subtract mass of the bullet, final velocity of the bullet from both sides. Oh, I'm sorry, I forgot to write one thing down. We do have the final velocity of the bullet as well. V final of the bullet. That is 125 meters per second. That's going to be very helpful. Okay? So let's solve for final velocity of the wood block. We're going to subtract this from both sides. And then we're going to divide by mass of the wood block. So it should look something like this. Final velocity of the wood block would be mass of the bullet, initial velocity of the bullet, minus this right here, mass of the bullet, final velocity, I'm going to make that B a little smaller, times final velocity of the bullet, okay, because we subtracted that from both sides. And all this is going to be divided by mass of the wood block, because this right here, we have to divide to get that away from V final of the wood block. Okay, well, all this stuff we know right here, so let's just plug in what we know. So that'll be the mass of the bullet, that is 0.075 grams, times initial velocity of the bullet, we know that too, 450 meters per second. Okay, minus mass of the bullet, again, same thing, 0.075 kilograms. Oh, I'm sorry, I put G's there. That should be kilograms in there. I put grams. We converted it to kilograms, so I might as well use kilograms. 0.075 kilograms. Sorry. That's the mass of the bullet times the final velocity of the bullet. We have that, we were told as well, 125 meters per second. All divided by mass of the wood block, 2.25 kilograms. Okay? So that'll give us our final velocity, V final of the wood block, because it's definitely going to be moving after a bullet shoots through it. So what is that? That looks like, if we multiply that, that is going to be 10.8 meters per second. Let's put a dotted line box around that, because that's not our final answer, but it's definitely an important answer, and it's certainly our goal for finding. In fact, I'm going to put a red. No, I won't. I'll just whatever. This was our goal right here, to find the velocity of the block for part A. So we've got that. Excellent. Let's come back to that. Let's just kind of put that on a shelf for now, and let's look at B. B is a little bit different question. And I need to check my time here to see how long we're going here. Not quite sure how to do that. Well, you know what? We're going to do B, and then I'm pretty sure I'm going to be running out of time, so we'll do C in the final video. But here's part B, and I'm going to kind of draw a line right here to separate these questions from the actual problems. B is asking, what is the net force acting to bring the block to a stop? Okay, well, if you thought about it before, if you slide something across the table, what's causing that object to come to a stop? Well, it's friction. So the net force, F net, is friction, or we would call that kinetic friction. Friction acting on an object that's moving. Okay? Well, if you recall, how do we calculate kinetic friction? This is where we take the coefficient of friction right up here that we had listed before. That's where we have mu sub k, that's that Greek letter m. That's our coefficient of friction. And if you recall, we take that times, you could say times the normal force, or times mass times gravity. That's how we calculate the coefficient of kinetic friction. That's going to be really important, because that's going to be the force acting against our the motion of our block. Okay, so let's plug that in and solve for what our kinetic friction is. So mu sub k, the coefficient of kinetic friction, that's 0.20, 0.20. And remember, there's no units, it's just a value, times the mass. What's the mass of this object that's moving? Well, that's the mass of the block, right? That's 2.25 kilograms. 2.25 kilograms. Mass of the W, I'll write that in there, mass of the wood block, times G, which is gravity, we all know that, that's 9.81 meters per second squared. Okay, and that'll give us our coefficient of kinetic friction, and I have my calculations right here. What is that? 4.41. 4.41 what? Well, if it's a force, it's got to be newtons. 4.41 newtons. So let's draw a dotted line box around that. That's really important. That's going to be the force bringing our moving block to a stop. And in part C, which is the final, I'm going to make a separate video. We're going to tie our velocity of the block after the collision and the force acting against it, friction, together to find how far this block is actually going to slide before coming to a stop. And it's going to use some older physics that we learned before, like kinematics, but I think you'll see it all come together in this next video. So look for you on the next one. We're going to do part C and finish this problem up. I'll see you then.